Okay, so well, it is an oracle. Did you see that thing that Kyle posted about the cartoon of like types of programmers?
Yes.
That was so good. And the closure guy had a man bun,
Yeah.
and and the Lua lady was like, "I'll take it from here."
I've never played with Lua, have you?
A little tiny bit. The Control 4 um, automation, the well, what they call the controller, which is basically the thing that interfaces with different pieces of AV equipment, and you like send it messages. The drivers that interact with the kind of um, support all the API for whatever piece of hardware that you're talking to, those APIs are written in Lua, and I've had to do a little bit of debugging on those. It's like XML in Lua,
Oh, okay.
but a lot of video game, like World of Warcraft, has a lot of Lua. It's a pretty, it's a cool language.
Yeah,
Pretty,
I just didn't really know what it was used for.
it's it's pretty C like. I think it compiles to C. There's something called like Love. That's like a Lua to JavaScript transpiler. That's what it's called. Yeah, it's used a lot for game development.
Oh, okay.
Maybe this isn't to JavaScript. It's just for like building games. So a lot of Android games. I don't know. Oh, there's a tree. All right. Seems like we start at 7:20 every time, which is cool. Start the reading. So sharing my screen. Everyone can see my screen. I guess um, if anyone wasn't here, like I told Danielle earlier, if you don't mind, whenever you're reading, just sharing your screen. That way, um, it it'll follow along more with the text. Um, just because that kind of fixes like later in the video, it won't be like you reading and just a picture of one of our faces.
But what if that's what people came for?
Maybe that is what people came for. That's a good point. So do whatever you want. Okay, so the first thing we're going to do is that naive Fibonacci. Just kind of looking ahead a little bit. Counting change example. Pascal's triangle. Cool. Okay. Yeah, we probably do like half of this. Oh, there's a lot of exercises because they're probably going to want to get into how to actually store or yeah, create some maps of the things that you've already computed.
Probably.
Cool. And then it'd be cool. What is it just called big O notation? Is that the common term for talking about um, time? Because they described it.
The technical term is asymptotic notation,
Okay.
but if you say big O notation, people will generally know what you're talking about.
Okay. Cool. I did not know that. Let's see. asymptotic. It seemed like they also talked about, like, it's usually given in terms of time, but then there's also a space calculation that can be made, which I guess is how
Yes,
much
there is.
memory.
Right. Or just the relative size as a function of usually the size of input.
Oh, okay. But the two wouldn't be similar. They're different things.
Right. And sometimes they're similar, sometimes they're not.
Cool. Should I start on tree recursion?
Go for it.
Okay, here I go. 1.2.2, tree recursion. Another common pattern of computation is called tree recursion. As an example, consider computing the sequence of Fibonacci numbers in which each number is the sum of the preceding two: 0, 1, 1, 2, 3, 5, 8, 13, and so on. In general, Fibonacci numbers can be defined by the rule fib of n is 0 if n equals 0, 1 if n equals 1, and Fibonacci of n minus 1 plus Fibonacci of n minus 2 otherwise. We can immediately translate this definition into a recursive procedure for computing Fibonacci numbers. See code example. Figure 1.5 is the tree recursive process generated in computing. The only kind of tricky part here is we're using the cond function, which we talked about last time, which is basically that a switch case. Consider the pattern of this computation. To compute fib of 5, we compute fib of 4 and fib of 3. To compute fib of 4, we compute fib of 3 and fib of 2. In general, the evolved process looks like a tree, as shown in figure 1.5. Notice that the branches split into two at each level, except at the bottom. This reflects the fact that the fib procedure calls itself twice each time it is invoked. This procedure is instructive as a prototypical tree recursion, but it is a terrible way to compute Fibonacci numbers because it does so much redundant computation. Notice in figure 1.5 that the entire computation of fib3, almost half the work, is duplicated. In fact, it is not hard to show that the number of times the procedure will compute fib1 or fib0, the number of leaves in the above tree in general, is precisely fib n plus 1. To get an idea of how bad this is, one can show that the value of fib n grows exponentially with n. More precisely, see exercise 1.13, fib n is the closest integer to what is that symbol? I don't know that symbol.
It's the Greek letter phi or phi if you want to get really
Oh,
fancy about it.
okay, phi of n over 5. Okay, so fib of n is the closest integer to phi of n over 5, where phi equals 1 plus square root of 5 over 2 equals 1, blah, 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 is the golden ratio, which satisfies the equation phi plus 1 equals phi squared. Cool, so they just dropped in some Euclidean geometry stuff.
They sure did.
Yeah. So we're all familiar with the golden ratio, probably from that Disney cartoon. But it's often considered the divine proportion, or it shows up in art constantly because it's a very pleasing ratio on the eyes. Thus, the process uses a number of steps that grows exponentially with the input. On the other hand, the space required grows only linearly with the input because we need keep track only of which nodes are above us in the tree at any point in the computation. In general, the number of steps required by a tree recursive process will be proportional to the number of nodes in the tree, while the space required will be proportional to the maximum depth of the tree. We can also formulate an iterative process for computing the Fibonacci numbers. The idea is to use a pair of integers a and b initialized to fib1 equals 1 and fib0 equals 0, rather, and to repeatedly apply the simultaneous transformations a toward a plus b, b toward a. I'm not sure how to say this left pointing arrow.
Me neither.
Yeah, I'm not sure. It's
I, it looks like
morphism?
it looks like some kind of assignment statement, maybe.
Oh, left arrow. That makes sense.
Like for the next call, you set a to equal to a plus b, and then you set b to a for the next
Oh, okay.
function call.
Yeah. So we're trying to not use recursion.
Not in the naive way. Well, we talked about this a little bit last time. What they're calling iterative, I would still call it tail recursive. That
Right.
because you've still got a function that calls itself, but it's not.
And you're kind of
It's not the
incrementing.
naive recursion.
Right. And so then you're kind of keeping track of the process. So we haven't gotten into memoization yet, but doing it
Yeah.
this
This
way
is
will fit.
a crude attempt of it. Pretty much anything that's tail recursive, you have to have some kind of accumulator as you're
Okay.
going.
Which is this count, I believe.
Right. So yeah, like in the case of the factorial function, it was your running product.
Right. Cool. I thought this was something on the screen, and it was just on my screen. Um, Thus, we can compute Fibonacci numbers iteratively using the procedure, C procedure. Probably, yeah, I think what we just said. We have this this extra argument called count, which just returns b if count is 0, and otherwise then it's recursive plus calling a decrement of the count of the count argument as the third argument to the fib iter. So yeah, I'm sure we'll see more of that in a second. This second method for computing fib of n is a linear iteration. The difference in number of steps required by the two methods, one linear in n and one growing as fast as fib n itself, is enormous, even for small inputs. One should not conclude from this that tree recursive processes are useless. When we consider processes that iterate on hierarchically structured data rather than numbers, we will find that tree recursion is a natural and powerful tool. Footnote 32. An example of this was hinted at in section 1.1.3. The interpreter itself evaluates expressions using a tree recursive process. Uh-huh. And that's something we can also look at later if we check out like Python Tutor or something like that, where it shows all the frames. But even in numerical operations, tree recursive processes can be useful in helping us to understand and design programs. For instance, although the first fib procedure is much less efficient than the second one, it is more straightforward, being little more than a translation into Lisp of the definition of the Fibonacci sequence. To formulate the iterative algorithm required noticing that the computation could be recast as the iteration with 3 state variables. Example, counting change. It takes only a bit of cleverness to come up with the iterative Fibonacci algorithm. In contrast, consider the following problem. How many different ways can we make change of $1 given half dollars, quarters, dimes, nickels, and pennies? More generally, can we write a procedure to compute the number of ways to change any given amount of money? This problem has a simple solution as a recursive problem. Suppose we think of the types of coins available as arranged in some order. Then the following relation holds. The number of ways to change amount, the number of ways to change amount A using n kinds of coins equals the number of ways to change amount A using all but the first kind of coin plus the number of ways to change amount A D using all n A minus D using all n kinds of coins, where D is the denomination of the first kind of coin. I say that one more time. The number of ways to change amount A using n kinds of coins equals the number of ways to change amount A using all of the first kind of coin plus the number of ways to change amount A minus D using all n kinds of coins, where D is the denomination of the first kind of coin. That would be difficult to understand by just hearing. To see why this is true, observe that the ways to make change can be divided into two groups. Those that do not use any of the first kind of coin, and those that do. Therefore, the total number of ways to make change for some amount is equal to the number of ways to make change for the amount without using any of the first kind of coin, plus the number of ways to make change assuming that we do use the first kind of coin. But the latter number is equal to the number of ways to make change for the amount that remains after using a coin of the first kind. Thus, we can recursively reduce the problem of changing a given amount to the problem of changing smaller amounts using fewer kinds of coins. Consider this reduction rule carefully and convince yourself that we can use it to describe an algorithm if we specify the following degenerate cases. Quick footnote. For example, work through in detail how the reduction rule applies to the problem of making change for 10 cents using pennies and nickels. If A is exactly 0, I think that's 0, but it's actually O. If A is exactly O, we should count that as one way to make change. If it is less than 0, we should count it as 0 ways to make change. If n is 0, we should count it as 0 ways to make change. We should count that. Okay. I'm kind of confused. What is A?
A is the amount you're getting change for, I believe.
Oh.
And then I think N is a list of denominations of coins that you have.
Oh, okay. I thought that was. And D is the denomination of the first kind of coin? Okay.
Right.
Okay. And CC here, I think, is count coin. Or
That would be my guess. Let's see. So it's defined in the next. So it's kind of like the fib iter thing. It's basically the helper function that does all the heavy lifting.
Yeah. I wonder. This is why you name your functions.
Right.
CC. I'll just call it CC. So this is a recursive procedure which takes the count change argument and amount and returns CC with the amount 5, because I guess 5 are the number of denominations that there are.
Right.
That's n. Okay. And then CC is defined by this. So it takes the amount, oh, right, kinds of coins. And then it asks, is amount equal to 0? If so, 1. Oh, or we haven't seen this yet. Or is amount less than 0, and then I'm not totally sure about the syntax.
Remember, it's prefix notation. So what it's saying is if the amount is less than 0 or kinds of coins is equal to 0, then your result is 0.
Oh, right. Okay, so these two cases.
Right. Those are your arguments to or.
Okay. Had we seen an or yet? I think this
I
is the first one.
think so, maybe not.
Oh.
I thought we had, but maybe I hallucinated it. So
I'm not sure. Anyway, well, there's an or we probably have. Um, okay, and then so if it's equal to 0 or less than 0, then kinds of coins, or okay, if amount is equal to 0, why is it returning 1?
yeah, because that's what it says. If amount is equal to 0, it returns 1. Because remember, it says if a is exactly 0, we should count that as one way to make change.
Right.
Then if an amount is less than 0 or the kinds of coins is equal to 0, then that's considered 0 ways to make change. So that's just phrasing that in scheme syntax.
Yeah. Okay, cool. Then okay, and then our other um, oh gosh. So our alternative, I had to look up the name of that. We add the result of calling CC with the amount of the decremented kind of coins to calling CC with a decrement of the first denomination, which is called here, which is just a switch case. That's basically a lookup table for the denomination. So like a penny is 1, a nickel is 2, a dime is 3, etc. And so the second argument to the sum is to call CC again with the subtraction of um, the kind of coin from the amount with, and passing in again the kind of coin. I'm having trouble visualizing this as a tree. I kind of see how it would be. So
I thought they'd show one later on, but it doesn't look like they do. But it's basically like, so let's see, how did they define it? Okay, so yeah, it's the sum of the number of ways to change amount A using all but the first kind of coin. And then the number of ways to change amount A minus D using all n kinds of coins, where D is the denomination of the first kind of coin. So let's say we're making change for $1, 100 cents, right?
mm-hmm.
So the number of ways is equal. So the first kind of coin would be pennies in this case, I guess. Um, so it would be the number of ways to change $1 using everything but pennies, plus the number of ways to change, um, what is it, 99 cents or whatever, A minus D. So 100, your A is 100 minus D using all n kinds of, plus the number of ways to change 99 cents using all of your coins.
Mm-hmm.
Does that make sense?
Yeah, yeah. I can see that now where you're subtracting um,
So the
the number
amounts
of ways.
you're changing keep getting smaller and smaller, and that's how your
Right.
tree is built.
Yeah. Cool. I wonder if we can display this.
Actually, I think I have it wrong. I think it does it in descending order by size. So actually, it would be how to change 50 cents, or how to change a dollar using like just 50-cent pieces plus, or what was it? The number of ways to change it. Okay, so the number of ways to change. So to change a dollar using all but 50-cent pieces, and then the number of ways to change A minus D, so 50 cents using everything, all the coins you have. So yeah, I was thinking that didn't sound right. So yeah, it makes more sense to start with the larger coins and work your way down.
Mm-hmm. Yeah, which is why it's so we're subtracting 1 from here to get our
Right,
next
right, yeah.
lowest.
Because I just realized the initial call is with 5, so it's starting with the 50-cent pieces, and yeah, you're decrementing it. So yeah, you're starting with
Yeah.
larger coins
So you
and
get
working.
2 and then 2 and then 4 and then the difference or the yeah, so you get so the first time with 5 we should get 2 for amount. And then when we call it again with 4, we should get 4 plus the 2 from before. So amount is then at 6. Right? Because we could use 50 cents and then two 25s to make a dollar.
Something like that. I,
Something
I
like
I wish I had like a chalkboard or something that I could
that.
could use to explain it.
Something like that. We should set up. Oh, that would be a cool thing to get. Like what like on Khan Academy, how they have
Yes, like
the
one of those
pen things.
the bamboo tablets, or I think they're called, or
Yeah.
something like that.
Oh, that would be awesome. Should look into that.
Totally.
Okay.
I'm sure they're super cheap too. Not.
Yeah. Maybe we can make one. You could do you could, if you had another webcam, you could just do like an overlay.
Yeah, I guess you could do that.
um, okay, I feel like I have a pretty good handle on this. I can keep going, I think. Does it sound good?
Sure.
The first denomination procedure takes as input the number of kinds of coins available and returns the denomination of the first kind. Here we are thinking of the coins as arranged in order from largest to smallest, but any order would do as well. We can now answer our original question about changing a dollar. The ways of counting change of a dollar are 292. Count change generates a tree recursive process with redundancies similar to those in our first implementation of Fibonacci. It will take quite a while for that 292 to be computed, and it did when I ran it over here. On the other hand, it is not obvious how to design a better algorithm for computing the result, and we leave this problem as a challenge. The observation that a tree recursive process may be highly inefficient but often easy to specify and understand has led people to propose that one could get the best of both worlds by designing a smart compiler that could transform tree recursive procedures into more efficient procedures that compute the same result. Interesting. We get a footnote. One approach to coping with redundant computation is to arrange matters so that we automatically construct a table of values as they are computed. Each time we are asked to apply the procedure to some argument, we first look to see if the value has already been stored in a table, in which case we avoid performing the redundant computation. This strategy, known as tabulation or memoization, can be implemented in a straightforward way. Tabulation can sometimes be used to transform processes that require an exponential number of steps, such as count change, into processes whose space and time requirements grow linearly with the input. Right? Hmm. Down. So now we have an exercise. Exercise 1.11. A function f is defined by the rule that f of n equals n. If n is less than 3, and f of n equals f of n minus 1 plus 2f of n minus 2 plus 3f of n minus 3 if n is greater than 3. Write a procedure that computes f by means of a recursive process. Write a procedure that computes f by means of an iterative process. Iterative. Transform this pseudocode into real code.
Basically.
So, do you have any particular way that you see that being written, or that you would like to write that?
I was pulling up Replit. I was gonna play with it, so I guess it's already got the starter code. Well, just the function
Yeah,
signature. So
your
I
code
just
here.
yeah. I mean, I guess you could use cond if you just wanted to keep it real simple.
Yeah.
Or actually, you don't even need. You can just use a good old if statement because there's actually only two possibilities.
Oh yeah, that's right. In less than 3 or in greater than 3.
Right.
What should we call the function?
Let's just call it f. Like, let's
F is
stick with.
good.
Yeah, that's no need to get fancy.
Cool. We need to specify else.
Um, you mean like using the keyword else? I don't think so.
What?
I mean, I have something that works. It may or may not be correct.
Hmm. Do you mind sharing your screen?
Not at all. Where's the
Woo!
here we go.
I have cannot read property car of undefined.
Okay. Can you see my screen?
Mm, not yet. Your icon's kind of grayed out though.
Okay, that's
You might have to install. Are you on Chrome?
I am not.
Oh, okay. Are you on Firefox?
I am.
Okay. It still let me share my screen on Firefox or like my browser window.
Hmm.
I just see at the top there's a start stop screen sharing.
Yeah. Oh no, I don't. I don't want to share that. Oy.
Let's see.
Hmm.
I'm gonna keep working on my.
Yeah.
I think I wrote. I don't think I wrote an if statement correctly.
Yeah. I can. Let's see. Actually.
I've written just a uh,
Okay, this is being weird. I'm gonna try something. I'll be right back. I'm gonna try and come back in Chrome. See if
okay.
this is will stop being weird. Okay, do you want me to try and share my screen again?
Sure. Yeah.
Let's see if we can get this to work. Oh, I have to install their extension. Wait.
It's not too bad.
Yeah. Okay. Okay. See if it'll let me show it. Can you see it?
Yep.
Yay! Okay.
Cool.
Bump this up a little bit so it's a little easier to see. But like I said, I make no claims as to the accuracy of this result, but I think this is what they were getting at. So we're defining f of n is if n is less than 3, then it's n, right? Is that the definition?
Mm-hmm.
And then otherwise, it's this, because remember, you can use the plus operator and then have an arbitrary number of arguments after it.
Right.
So the first thing is f of n minus 1, and then 2 times f of n minus 2, and then 3 times f of n minus 3, and then a whole bunch of parentheses.
Yeah.
So that's the my understanding is that's the recursive way.
Cool. Yeah, that looks perfect. I tried to do that and ended up with something just
okay.
Not quite there. Just got... Oh. Well, I got a number out, but I don't think that's...
Woohoo!
I just get 2 every time. If n is less than 3, so it should just return n, right? Well, it works for the first case.
Oh, you need another parenthesis after f of n minus 1. You need another parenthesis there.
Oh, good catch.
And then you can probably trim one off the end.
Yeah. Yeah. Okay, I think that's right. Do you get 38 if you do f of 5?
Let me see. I get 25.
Okay. I bet I have more things wrong.
Yeah.
Times 3. Then minus 2.
Actually, I have an idea how we might be able to see if we're getting anything approaching accurate solutions.
Oh, in the teacher's handbook?
No, that's although I guess I could look at that, but that wasn't even I totally I didn't forget I had it, but that's not what I was thinking. So. Although now that you mention it,
Can always take a little peek.
Well, although, well, remember I told you not too long ago that I don't think it actually has like solutions for a lot of for like maybe any of them, the problems. So
right,
it just has like examples and what have you. Okay, square roots by Newton's method.
Whoops.
Okay, so tree recursion. Okay, yeah, it's not gonna help. No, I was actually I actually had a much blunter instrument in mind.
Do tell.
Excel.
Oh, Excel. Let's do it. Let's spin it up.
So yeah, because we already have like numbers, right? So we know that the first, so if n is less than 3, then it's n. So if we have, if we fill a series from like 1 to whatever, so the first values are going to be 1 and 2, and then the others we can do as formulae, right? So so it is equal to, where'd that definition go?
Oh, I found another parentheses I was missing. Okay, it's you get 5 is 25.
Yes.
Okay. Yep, and 6 is 59.
Let's see. Yes.
Okay, cool. Yeah, I was just missing another paren. So
but I want confirmation. Right?
yeah,
Like
yeah.
this is totally bugging me. So
Yeah.
Okay.
I'm also
Here we go. Okay. So equals. Wait. Okay. So equals the row above it plus 2 times 2 rows above plus 3 times 3 rows above. So you actually have to start your sequence with 0. So yep, so yeah, f of 5 is 25, f of 6 is 59, f of 14 is 60,104 if anyone cares.
Oh wow. Okay.
So
yeah.
Yay, Excel. It can be useful.
Oh, definitely. It seems actually. Ooh, 18 took a while. 14 didn't take very long to compute, but
Yeah.
18
Let's see.
took a minute. 1,910,507.
Oh, okay.
That's where we're hurting someone's server.
Yeah. So yeah, f of 20 is that 10,771,211.
Wow. So this is growing. How do we describe that growth? Because it's creating new f. It's creating 3 new f functions every time.
Right. So, is it 3 to the n? I don't know. So that would be my guess. It would be like somewhere in the neighborhood of 3 to the n.
Yeah.
What is this? It's how do you do exponents in Excel?
You can Google it.
Yeah, I am doing that right now. Okay, power. Okay, so.
Oh, caret, I think.
No, there's actually
Oh, there's a POW function.
power. Yeah, power. So let's see. Okay, maybe not quite. Well, it might be 3 to the n divided by something. So.
So that's the recursive way. And then the second problem it asks to write an iterative process.
I think we should leave that as homework. Otherwise, we'll be here all night.
Yeah, let's do that.
Okay. I mean, some people might be into that, but
nah, that's okay.
Welcome to Dan and Danielle's all-night scheme hangout.
Yeah, it just never ends.
The swingingest place on the interwebs.
It's more like a Maria Abramovich performance art, where we're just like looking
there we
at
go.
the screen and, like, crying. Yeah. Okay, so do you feel like going on to exercise 1.12?
Um, we can at least give it a go.
Okay. So looks like the following pattern of numbers is called Pascal's triangle. The number at the edge of the triangles are all 1, and each number inside the triangle is the sum of the two numbers above it. I didn't know that had a name. I used to draw that a lot.
Oh,
Um,
there you go.
cool. And then we get this footnote. The elements of Pascal's triangle are called the binomial coefficients because the nth row consists of the coefficients of the terms in the expansion of x plus y to the n. This pattern for computing the coefficients appeared in Blaise Pascal's 1653 seminal work on probability theory, Trait du triangle arithmétique. I apologize to everyone. According to uh, Knuth, 1973, the same pattern appears in Suyin Yuqin's The Precious Mirror of the Four Elements, published by the Chinese mathematician, I'm probably butchering this too, uh, Chu, Chu Shi She in 1303. In the works of the 12th century Persian poet, and I should not have tried reading any of this, mathematician Omar Khayyam, and the works of the 12th century Hindu mathematician Bhaskara Acharya. 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 Bhaskara Acharya. Okay. I'm so sorry. Oh boy. So it appeared, this same pattern appeared many times throughout history: 14th century, 17th century, and 20th century, and the 12th century. Oh boy. Write a procedure that computes the elements of Pascal's triangle by means of a recursive process. If a number lies outside of the triangle, return 0. This makes sense if we view Pascal as the combination function, start counting rows and columns from 0. So combination function. In mathematics, a combination is a way of selecting items from a collection such that, unlike permutations, the order of selection does not matter. In smaller cases, it is possible to count the number of combinations. For example, given 3 fruits, say an apple, an orange, or a pear, there are 3 combinations of 2 that can be drawn from the set: an apple and a pear, an apple and an orange, or a pear and an orange. More formally, in k combinations of a set S and the subset of k distinct elements of S, a k combination of set S is a subset of k distinct elements of S. If the set has n elements, the number of k combinations is equal to the binomial coefficient. Okay. But they're suggesting that we view this as a combination function. Your code here. So I'm going to just use the staring method and stare at this.
Okay. Yeah, yeah. Me too.
Write a procedure that computes elements of Pascal's triangle by means of a recursive process. So above it is a little bit of a misnomer because it's kind of this zigzaggy thing, where
Right.
5 is the sum of 4 and 3, 4 is the sum of 3 and 2,
Mhm.
and 10 is the sum of 6, 3, and 1, or 4 and 6.
Or
Oh,
four
I
and
guess that's
six.
what it
Yeah.
means right above
So
it.
yeah.
But it's also kind of this pattern. Okay.
So
So we can memorize, or is that what it's asking?
let's see. Let's start with the recursive way, and then if because that would be easier. So if um, so if the column equals 0, then the result is always 1.
Mm-hmm.
And then if it does have to yes, it says if a number lies outside of the triangle, then you have to return zeros. So if you have something like
Like row 1, column.
so like yeah, like row 1, column 5 or something like that, that would be 0. So
Start counting rows and columns from 0. So this,
right. So this 1 at the top would be row 0, column 0.
okay,
And then the next one, the next row down is row 1, column 0, and then row 1, column 1.
okay. Row
So
2, column 0, column 1, column 2. Okay. So how, I'm just going to think about what's the Pascal of row 3, column 3.
right. So if let's see, let me
It's going to be 1.
right, yeah, row 0, yeah. What is it? Row 3, column 3? Yes.
So, and
And
it's,
that's another thing. If row and column are equal,
mm-hmm.
then it's always going to be 1.
Oh, yeah. Okay. And then also if it's 0, it's 1.
Right, yeah. So if the column is 0 or it's equal to the row, then your result is 1.
So those are two base cases where we would return 1.
Right. Okay. So just okay. Or column is equal to 0, then you can return 1.
Okay, so we can use that or.
Use that or, yeah. Otherwise, it's the sum of the row minus 1, column minus 1, row minus plus row minus 1 column. I think. Include the sum in there.
Right, because you're adding.
Right.
That's fine. I'm like, I'm not sure if I'm even getting this or statement right.
Yeah. Let's see, let me try and call an example. So 0, 1, 2, 3. Okay. It looks like there's something wrong with my syntax. Hmm.
Do you want to share your screen, Daniel?
Yeah, sure. Yeah, I was going to say this is probably riveting stuff for people who are listening. So,
I'm just struggling with the grammar.
yeah. Let's see. Let me. Okay, so I've got it's not returning the correct result, but so I've got define Pascal row column. Maybe you can see what's going where I have a parenthesis placed wrong, probably. So it seems like a con statement, right? So if the column is greater than the row, we return 0.
Mm-hmm.
And then if the column is equal to 0 or the column is equal to the row, then it's 1. Or otherwise, it's the sum of the Pascal of row -1, column -1, and Pascal of row -1 and column. Actually, just real quick, let me reverse these to make sure it returns 0 when it should. Okay, that's odd.
Hmm. I wonder if you need those. Yeah, right where your cursor is. I wonder.
Yeah, I was
if you
gonna
need
say,
that.
maybe, did I overdo the parentheses? Maybe. Let's try that. Oh, nope. It says what?
Yeah, that's a JavaScript.
Oh, okay. Hmm. Okay, yeah, because I was looking up con syntax, and it looks like you do need them for the. Okay,
Oh yeah.
okay, let's put those back in then.
What if you need the or?
Um. Well, let's try simplifying things a bit then. Wait a minute, are those in the right place? Let's see what that does. Okay, now see, that's weird.
Mm-hmm.
It should at least return.
Maybe that last statement.
Yeah.
So you're asking.
Or maybe do I have them in the wrong order? Let's see.
Well, it should just be returning 0.
Oh, no, that's okay. No, I had it right the first time. But yeah, it should be returning 0. That's so weird. Oh my god.
Is it gonna return 0?
Hmm.
Because it's gonna call. It's gonna do that last. Um, the last statement.
But it shouldn't even get there, should it?
I think it will.
Because right now I've because I purposely called it with a column greater than the row. So if that's the first condition, it should just return
Right,
the result.
right.
So
Yeah, I didn't see where you were switching.
yeah.
Yeah. Yeah, that should. Should just return 0. Let's see.
Okay. At least some of it's working.
Oh, nice.
Okay, so that's working. Hmm. Or maybe that might be right. No, it's not. Okay, I didn't think so. 0, 1, 2, 3. Yeah, so it should be 3. Shouldn't be 1. I think it's something in this 0 thing that it's not returning as it should. I think that's what's throwing everything off.
Hmm.
It's getting really dense. And
So intense. Um, where's the order? Whoops.
yeah, I was wondering about that too, actually. But it seems like that's how, like if I were writing this in any other programming language, this is the order I would put them in. So, because you check your error cases first, then your base cases, then your recursive calls if applicable.
Yeah. No, that makes sense. I wonder if it's the that actual formula at the end.
Yeah, that's that's let's see. So, okay, so plus Pascal. That's the first parameter. Okay, that's the first argument. Plus, and then plus Pascal. Huh. That is so weird. Yeah, it's got to be something with the syntax. Okay, I'm actually gonna erase everything and type this back out. Okay, cond greater than.
Oh, I just found a walkthrough.
Yeah.
Yeah. I don't know if you want to look at this.
Let me try and get through this, and if my reconstituted version doesn't work, then we'll take a look at it.
Sounds perfect.
Okay, let's take a look at the walkthrough.
Okay.
I'll stop sharing my screen.
Well, one thing is maybe having an else at the end.
Do we need to have an else? Oh, you totally do. Oh my goodness, I feel like such a goofball.
Is that it?
It might be.
Try that because I'm pretty sure your math was right.
Yeah, right. Okay. Oh my god.
That was it?
I'm pretty sure that was it. Yeah, I didn't include. I see it was something with my syntax.
Yeah.
Okay, so all right, let me make
Cool.
sure that this returns. Although it's weird that it doesn't actually print out 0 in any of the cases that it returns 0. That weirds me out a little bit. But whatever. I'm not gonna.
Yeah.
Yeah, it's.
Do you mind sharing your screen?
Oh, not at all. Let me bring that back up. Okay. All right, here we go.
Cool.
And so yeah, so Pascal like 3.1. If we run it, gives us 3 as it should. So
that's 3 colon 1. Cool. Yeah. So if you did like 3-4,
it should be. It would just not give you anything. For some reason, it doesn't print out 0.
That's a little strange.
Right?
Yeah.
Yeah, there's probably something in the syntax there too, but I ain't got time to mess with it. Or actually, let me try surrounding it with another set of parentheses, see if it does anything. I don't think it will, but oh no, it doesn't like that. So fine. Okay.
Wonder what.
Okay, so 1, 2, 3. Okay, so yeah, it gives us 10 as it should. Okay. All right, that weirds me out that it won't print out the 0, but whatever.
Yeah, I wonder if it has anything to do with maybe treating 0 like false, or what would happen if you wrapped the 0 like as a string?
That's a good question. Oh wait, oh, it helps if you have to call a. Oh, okay, there we go. Oh, okay, that's.
So it's kind of treating it like false.
It might be. Let's see. Okay, that's interesting.
That's really, yeah.
Yeah.
I didn't know about that.
Yeah, I wonder if that's a quirk of this particular.
Could be.
Yeah, REPL. Like if I fired up my actual scheme interpreter, I wonder if it would do that. Oh.
Are you using Dr. Racket?
No, I actually have MIT scheme installed on my command line.
Oh, nice.
So, I mean, we can check. We can test this hypothesis real quick.
Let's go for it.
I'm a pretty fast typist, so. Or actually, I wonder if it'll let me copy and paste. That would be amazing.
Probably.
Okay. Okay, see, now there it returns a proper 0.
Yeah.
Okay.
So that's something to do with that REPL.
Okay, yeah, okay. I feel better now. I can sleep tonight. Okay.
Do you mind actually copying that into the chat real fast?
Not at all.
Oh.
I think, well, there's actually a document thing that you can use. I wonder if it'll let me do that.
Oh, yeah.
I'll stop sharing my screen. So otherwise I'm getting this like infinity thing.
Document. Right.
Okay. So. Oh, okay. Now it's doing all this weird stuff. But you can get the idea.
Yeah. I think that'll still work.
Yeah.
Oh, it's using Etherpad.
Yeah, which I'm not familiar with, but.
Oh boy. This is.
Yeah, it's a little rough.
I could fix this.
Maybe actually let me try to type it into the chat. See if that does.
Oh, it's okay. Oh, that's perfect. There we got it.
Yeah. So.
Okay, and that should be, yeah, we get 1. And then I'm just going to do 0 as a string.
Yeah. That's so weird.
Will it? But it returns 1. 1 does work.
Yeah.
Maybe we can report an issue, because I think they are on GitHub.
Yeah.
Yeah, they are.
Oh, okay.
And it doesn't appear to be an open issue yet.
No.
I'm just gonna mute my. I'm gonna mute myself.
So I guess, Jeff, do you have any questions? Or?
Jeff. Sure. I just opened an issue.
Yeah.
Okay.
Cool.
Cool. What is this? What is section 113? Prove that fib of n is the closest integer to 5n over square root of 5.
Let's not and say we did.
Yeah. Homework. Ooh,
Yeah. Yeah. Maybe.
Question mark, maybe.
Yeah.
Okay. Orders of growth. Do you feel like reading, Daniel?
Sure, I can. Okay. Orders of
Do you
growth.
mind sharing?
Oh, yeah. Sorry, forgot.
No worries.
Here we go. Application window. Actually, I just share the entire screen. That's fine. Okay. Orders of growth. The previous examples illustrate that processes can differ considerably in the rates at which they consume computational resources. One convenient way to describe this difference is to use the notion of order of growth to obtain a gross measure of the resources required by a process as the inputs become larger. Let n be a parameter that measures the size of the problem, and let R of n be the amount of resources the process requires for a problem of size n. In our previous examples, we took n to be the number for which a given function is to be computed, but there are other possibilities. For instance, if our goal is to compute an approximation to the square root of a number, we might take n to be the number of digits accuracy required. For matrix multiplication, we might take n to be the number of rows in the matrices. In general, there are a number of properties of the problem with respect to which it will be desirable to analyze a given process. Similarly, Similarly, there we go. R of n might measure the number of internal storage registers used, the number of elementary machine operations performed, and so on. In computers that do only a fixed number of operations at a time, the time required will be proportional to the number of elementary machine operations performed. We say that R of n has order of growth f of n, written R of n equals theta of f of n if there are positive constants k1 and k2 independent of n, such that k1 times f of n is less than or equal to R of n, which in turn is less than or equal to k2 of f of n for any sufficiently large value of n. In other words, for large, what's that? In other words, for large n, the value R of n is sandwiched in between k1 times f of n and k2 times f of n. So basically, it's a really fancy way of talking about upper and lower bounds here. So,
Okay.
For instance, with the linear recursive process for computing factorial as described in section 1.2.1, the number of steps grows proportionally to the input n. Thus, the steps required for this process grows as theta of n. We also saw that the space required grows as theta of n. For the iterative factorial, the number of steps is still theta of n, but the space is theta of 1, that is constant. And we have a footnote here. These statements mask a great deal of oversimplification. For instance, if we count process steps as machine operations, we are making the assumption that the number of machine operations needed to perform, say, a multiplication, is independent of the size of the numbers to be multiplied, which is false if the numbers are sufficiently large. Similar remarks hold for the estimates of space. Like the design and description of a process, the analysis of a process can be carried out at various levels of abstraction. The tree recursive Fibonacci computation requires theta of phi to the n steps and space theta of n, where phi is the golden ratio described in section 1.2.2. Orders of growth provide only a crude description of the behavior of a process. For example, a process requiring n squared steps and a process requiring 1000 n squared steps and a process requiring 3n squared plus 10n plus 17 steps all have theta of n squared order of growth. On the other hand, order of growth provides a useful indication of how we may expect the behavior of the process to change as we change the size of the problem. For a theta of n, i.e. linear process, doubling the size will roughly double the amount of resources used. For an exponential process, each increment in problem size will multiply the resource utilization by a constant factor. In the remainder of section 1.2, we will examine two algorithms whose order of growth is logarithmic, so that doubling the problem size increases the resource requirement by a constant amount. Exercise 1.14. Draw the tree illustrating the process generated by the count change procedure of section 1.2.2 in making change for 11 cents. What are the orders of growth of the space and number of steps used by this process as the amount to be changed increases? I don't really know if we have the means to
Draw a tree.
show that process in a meaningful way.
We can probably talk about it.
But yeah, we can kind of at least verbally talk through some of it, like which we kind of did when we discussed the problem, right?
Yeah, I think so.
So like the largest, denominator of coins in this case would be a dime, right? So. But so it would be all the ways you can make change for 11 cents without using dimes, plus the number of ways you can make change for, so the amount is 11 cents minus, so the amount of change you could make for 1 cent in this case using all the coins you have.
Right.
Did that make sense?
Yeah.
And so that's, well, obviously that, that part of the tree, that's, well, there's only one way you can make change for 1 cent, right? So,
right.
So now we've got all the ways to make change for 11 cents without dimes. And so you would break that down into like nickels and pennies and so forth.
So the processes generated are going to be those paths, kind of what you just described.
Yes.
Okay. I have a really good sense of what I need to review this week.
You and me both.
Let's see.
Okay, so do you want to go ahead and move on to the next exercise?
Yeah, I think so. I think we did that earlier.
Yeah. Okay. The sine of an angle specified in radians. Is anybody confused by the term radians as opposed to degrees? I'll take that as a yes.
Yes.
Okay, that's fine. This is a judgment-free zone. Okay. So a circle in degrees is 360 degrees, right?
Mm-hmm.
In radians, it is 2 pi. So pi is 180 degrees, pi over 2 is 90 degrees, and so on and so on. So
Google's telling me that 1 radian is 57.2956 degrees.
Right.
Which makes sense because it's around 6.
Yeah, and I was going to say if you multiply that by 2 pi, then you will get 360 degrees. So
cool. Okay. Okay.
So yeah, that's for like if you take in calculus, stuff like this is almost always calculated in radians. So just a heads up.
Cool. Yeah. Thanks. When I get to calculus.
Yeah, I was gonna say when you get to calculus, just be prepared to do things in radians. It's actually it's actually easier, at least in terms of pencil and paper, to do it in radians. So because as you may have noticed, like math majors hate calculators. And it's because there's a loss of precision. No matter how many decimal places your calculator has, it's only going to be an approximation of a number like, say, pi.
Right.
Whereas pi is pi.
Yeah.
That's the exact amount. And so pi over 2, you're writing pi over 2, then that's the exact amount, pi over 2.
Yeah.
Follow? Yeah. So
yeah, totally.
So that
makes sense. And 360 is kind of like throws off our units a little bit.
Right.
Like
our
radix.
Yeah. Radians are typically preferred for that reason.
Cool.
Okay. So, all right. The sine of an angle specified in radians can be computed by making use of the approximation sine of x equals x if x is sufficiently small, and the trigonometric identity sine of x equals 3 times sine of x over 3 minus 4 times sine cubed of x over 3 to reduce the size of the argument of sine. For purposes of this exercise, an angle, is considered sufficiently small if its magnitude is not greater than 0.1 radians. These ideas are incorporated in the following procedures. Define cube of x the way you normally would. Define p of x, that's the x over 3 and all that. And then define sine angle if it's not the absolute, if it's not greater than the absolute value of the angle. If the absolute value of the angle is not greater than 0.1, just return the angle. Otherwise, p of the sine of the angle divided by 3. Okay. So how many times is the procedure p applied when sine 12.15 is evaluated?
So how many times is it dividing by 3?
Right. Okay. So
So until it gets to 0.1.
right.
I'm going to say 7.
Sure. Let's see. Nope.
So,
The text disagrees.
yeah. I would oh, but I guessed 5 and that was right.
Oh, okay. Well, there you go. Yay.
Yay.
Okay. So, what is the order of growth in space and number of steps as a function of A used by the process generated by the sign procedure when sign A is evaluated? So,
My
I,
goodness.
I would.
Are we going to
So,
utilize this theta function up here?
what do you
No.
mean? Well, because remember, theta is just a boundary.
Oh,
So,
right. Oh, okay.
like, what function in here best approximates the growth of the function we just looked at? So, you only got 5 choices. So.
Yeah, okay. As a function of A used in the process generated by the sign procedure when sign A is evaluated. Well, we're dividing. Yeah. My intuition was that it was log n, but I can't totally tell you why, but that is right.
Yeah. Well, generally, when you're dividing something into like the same size number of pieces, it over and over again until you get down to a base case, that's usually log n. Like merge
Okay.
sort is probably the most famous example. You keep dividing the list in half over and over again until you have n lists of size 1, and that takes you basically you divide the list a total of log n times. That's how many times you go through that division process, right?
Okay. Yeah.
So
That's how many times. That's making sense. There's a really loud motorcycle outside.
yes, I noticed.
I It's so peaceful in my room.
Yeah, I was afraid I was going to have to move to a different room, but the next to last person in the lab left a few minutes before we started.
Oh, cool.
So
Yeah, you'll have to give me a tour of the lab sometime.
yeah,
That'd be cool. Yeah.
I think that's a good stopping point.
Oh, it is 9. Yeah, I think that's
Yeah,
great. And then we can start up with exponentiation next week.
yeah.
Cool. Um, so I'm gonna give myself some homework because
Mm,
I didn't
me too.
feel super grasp, but like I had a great grasp of a lot of this. So
Right.
I'm gonna look more at grammar of cons, else, or, and.
Yeah, I suspect it's like anything else. I just have to get used to writing a bunch of scheme programs, and then it'll become more natural to me.
Yeah, samesies. Okay, and then also radians.
Yeah.
um, the bounds, upper and lower bounds. Um, I'm more on Big O. review bingo. Review bingo. In greater detail. Cool. I kind of want to start or do kind of blog posts
Okay.
based on these.
Okay.
Like this one, which is really just the notes that just the notes from these meetings.
Okay.
Yeah.
Seems like a good idea.
For some reason, my the nav on this theme that I'm using is still kind of messed up.
Mm-hmm.
Oh, what's there?
What did you say you used for that again?
It's Hugo.
Okay.
Hugo. Static. Yeah, it's gohugo.io.
Okay.
It's pretty good. There's a couple there's a couple things that were kind of tricky, like installing the theme, and
Mm-hmm.
because your theme, the easiest way to do it is to just clone whatever theme that you want to use into your themes folder, and then you make that a like a Git sub module.
Okay.
So when you publish it to like GitHub pages, Git knows to go to that other repository and pull in that code,
Interesting.
or to point to it at least
Okay.
whenever it does the build. And then getting the syntax highlighting was a little. I mean, it wasn't that bad. I had to upgrade the syntax highlighter that they were using.
Okay.
But I like this theme because I can just basically copy it from Atom, and it looks pretty similar.
That's handy.
Yeah. So I'll put all my notes from the lecture as well.
Cool.
Yeah, I got some more today because he was talking about Towers of Hanoi,
Oh yeah. That's a classic.
Hanwha. So next week we exponentiation and
Woohoo!
mini exercises.
Yep.
Good.
So might want to look at those in advance.
Yeah. Testing for primality.
Ah. Wonder if it's the Civa Veritosthenes.
It's kind of funny that, or it's good. Like I like that we're looking at all these procedures that are very computationally expensive,
Mm-hmm.
because it's making me more aware of the code that I write.
Right.
Uh, and I think through getting through this chapter, we'll have a couple more kind of tricks up our sleeves to
Yep.
start doing things more efficiently.
Totally.
Yep. Well, is that a good stopping place?
I think so.
Okay. I'm going to stop the stream.
All right.
Goodbye, stream.